Hello everyone. So today we shall discuss problems on the Brayton cycle. We shall take example problem from Jan 2019 which says as follows. A gas turbine unit has a pressure ratio of 6, that means P2 by P1 or P3 by P4 is given as 6, this particular thing. The maximum cycle temperature is 610, that is T3, maximum cycle temperature T3 is given, converted into Kelvin, it is 883 Kelvin. The isentropic efficiency of a compressor and turbines are zero point 0.8 and 0.82 respectively. So efficiency of compressor is given, efficiency of turbine is given. Calculate the power output. So we need to calculate here what is the power output from the turbine. When air enters the compressor at 15 degrees Celsius, where does the compressive process start? From 1 to 2. Air enters the compressor at 15 degrees Celsius in the sense it is T1, this particular thing. So T1 is 288 Kelvin, converted into Kelvin again. At the rate of, this is the mass flow rate of air, which is 16 kgs per second. Take Cp is equals to 1.005 and gamma is equals to 1.4 for compression, and Cp is equals to 1.11 and gamma is equals to 1.333 for expansion process. So different values of Cp and gamma for the compression and expansion process are given. Now, since the efficiency of compressor and efficiency of turbines are given, you have to assume that it is a actual Brayton cycle. That means the process is going from 1 to 2 dash, not 2, and 3 to 4 dash, not 4. Okay, so that you have to keep this in mind. So the power output is generally given by the mass flow rate into the net work done. So net work done is a addition of the turbine work as well as the compressive work. Now, what is turbine work? It is given by mCp delta T. I told you Brayton cycle is a open system process, so you have to take these formulas mCp delta T. That too delta T being it is a work, so it is initial minus final, so T3 minus T4 dash. Again, I need to come back here. So what is the work done by the turbine? That is WT. Initial is 3 and final is not 4, it is 4 dash because of the efficiency being given. Similarly, what is the work done from the compressor, which is 1 to 2, initial minus final, mCp T1 minus not T2, it is T2 dash because the efficiency of the compressor is given. Okay. So similarly, work done by the turbine is given by Cp times of T3 minus T4 dash. See, you are eliminating m just because you are multiplying at the end. So at the end you are getting it as m dot into the net work done. Net work done Cp into delta T will give you the values in kilojoules per kg. So if you multiply by mass, it will be in mass by second, then it will be in kilowatts. We shall see that later. Don't worry about it. So as of now, as you are multiplying the mass flow rate at the end, so you are eliminating m here. That's it, simple. Okay. So T3 value and T1 value he has given. So T3 is 883 and T1 is 288. He has given the values. But we need to calculate what is T4 dash so that the work done by the turbine can be calculated, and we need to calculate what is T2 dash so that the work done by the compressor is calculated. So first we shall find T4 dash. Okay, or T2 dash, both the things. So for T2 dash, we will take one process 1 to 2. Process 1 to 2 is what is adiabatic compression. For this particular process, what we'll be doing is we'll be applying the PVT conversion equation, which states P1 by P2 is equals to V2 by V1 whole to the power of gamma, that is equals to T1 by T2 whole to the power of gamma divided by gamma minus 1. P2 by P1 is beta, so here it is P1 by P2, it is 1 by beta. So T1 by T2 whole to the power of gamma divided by gamma minus 1. Beta value was 6 and T1 value was 288 and the gamma value is 1.4 for the compression. So substitute everything, only T2 is unknown, T2 is calculated as 480.53. Now, once the value of T2 is known, now we have to calculate what is T2 dash. For this particular T2 dash, we'll be using the efficiency of the compressor. Okay, so efficiency of the compressor is given by isentropic work divided by actual work. Isentropic is ideal because it is T1 minus T2. That's why it is T1 minus T2. Actual work is actual, so T1 minus T2 dash. Okay, so efficiency of the compressor is 0.8. T1 you know, T2 you know, T1 you know, again T2 dash can be calculated very easily. So T2 dash would be 528.66 Kelvin. Once you got the value of T2 dash, you can calculate the compressive work output. So work done by the compressor, that is given by Cp into T1 minus T2 dash. Substitute the things and remember Cp value was 1.005 for the compression. Okay, so when you substitute it, we'll get the value of WC as minus 241.86 kilojoules per kg. Okay. Next, we will apply the same thing for the process 3 to 4, which is turbine work. Adiabatic expansion happens over there. For adiabatic process, what is a PVT conversion equation? It is P3 by P4 is equals to V4 by V3 whole to the power of gamma, that is equal to T3 by T4 whole to the power of gamma divided by gamma minus 1. What is P3 by P4? It is directly beta. T3 by T4 whole to the power of gamma divided by gamma minus 1 I am taking here. Beta value is 6, T3 value is 883 and gamma value for the expansion is 1.333. Substitute those, only T4 is unknown, so calculate T4 as 564.37. This is not end, you have to calculate T4 dash because the efficiency of the turbine being given. Efficiency of the turbine is equal to actual work divided by theoretical work or isentropic work. So actual work is what? Where a dash is involved. So T3 minus T4 dash. Theoretical work is where ideal process is involved, which is just T3 minus T4. Substitute the things. 0.82 is your turbine efficiency, T3 value is 883 and T4 value is 564.37. When you substitute everything, only T4 is unknown in this equation. So T4 dash is calculated as 621.72 Kelvin. Once T4 is known, you can calculate the turbine work Cp minus initial minus final, T3 minus T4 dash. So Cp value for the expansion process is 1.11. Substitute it, you will get the turbine work output, that is WT. So the net work output is turbine work plus compressive work. So 290.02, which is turbine, minus 241.86, which is the compressive one. So add these two, you'll get the value of net work done, which is 48.16 kilojoules per kg. Okay. Now, once you got the net work done, multiply it with the mass flow rate of the air. So that is 16. You will get 770.56 kilowatts. How will you get kilowatts? You can just analyze. Mass flow rate is given in kgs per second and net work output is kilojoules per kg. Kg goes away and kilojoules per second. Joules per second is watt, so kilowatt. Okay, so the work output from this particular gas turbine is 770.56 kilowatts. So this is the end of the problem. I so request you all to solve this particular thing. Take it down in your notes and solve this. And if you have any doubt, you can contact me. Okay.